brings tonight, the Nathan Seiberg is going to be telling us about what is quantum field theory.
Thank you. I'd like to thank the organizers for inviting me to speak here. Something bad with the sound.
It's okay.
Fine, yeah.
I hear myself twice. And I have the same problem that Costas faced. I received clear instructions not to talk about things I understand, to keep the discussion broad, accessible to people from different fields, and so forth. But yesterday I saw the talks, people actually had some ideas. And so I decided to rewrite the talk. So I'll really have two separate talks with a bridge between them. So hopefully that would be okay. Let's bring, yeah.
Follow my advice for the title.
That's the next point I was going to make. I actually copied Lars. Not only did he give me instructions, he also gave me a title. The title was Quantum Field Theory is Not What You Think It Is. And I decided to pick this one. I actually have something to say about titles. There's a known rule about titles. When there is a question in a title, the answer is always no. So this is well known. But what about questions like that are not yes-no questions? So I'd like to extend the previous rule. When there is a question like that in the title, which is not a yes-no question, the answer is always, I have no idea. So this is what I'll show you today. I'll discuss this thing. I apologize to some people in the audience might have already heard earlier versions of that, which were more condensed. I talked about that in the 2011 Solvay meeting. There was a 5-minute presentation. It went up to 20 minutes last December at Stanford. And now I was asked to talk for about an hour. And despite the more time, I still don't know the answer to this question. So I'll start with an overview of quantum field theory. So quantum field theory is very successful. Sorry? Oh, yeah, no, that's for sure. In fact, I'll give evidence that it exists. So quantum field theory is the natural language of physics. It works in a wide variety of circumstances, ranging from particle physics, condensed matter physics, cosmology. I'm sure we'll hear about it in the cosmology talks in this meeting. It's also used in string theory and quantum gravity. There's no question that it exists. There's no question that it is deep. I'll give more evidence that it is deep. It also has applications not just in physics, but also in mathematics, especially in geometry and topology. And so it's the natural language to describe diverse phenomena. There's been enormous progress over the past decades, and it's still continuing. That's a sign of a vibrant field that exists. And I'd like to emphasize that there are indications that it should be reformulated. So I'd like to make an analogy between calculus and quantum field theory. And there are many reasons to think about this analogy. First, the new mathematics is involved. That was the case in the case of calculus. It was motivated by physics. Newton wanted to understand the motion of bodies. But then it found applications in all sorts of other things, just like quantum field theory. Application in mathematics, physics, in other branches of science, even economics and engineering. And I think that all that is telling us that it is a deep idea. Nobody is going to argue that calculus is not a deep idea. And calculus is a mature field. It's a mature field. One sign I'd like to propose a test for a mature field. A mature field is a field that all textbooks are more or less the same. And all courses taught on the subject are more or less the same. It converges. It has been streamlined. That's the way to teach this. And if look at the quantum field theory course here at Stony Brook, and in Princeton, it will follow more or less the same order. Whoops. Moving to, what did I do wrong? So moving to quantum field theory, I copied the previous slide. The beginning is more or less the same. We have new mathematics. In fact, it's not yet rigorous. So it's so new that it doesn't yet exist. So that's the same as in the case of calculus. It's new mathematics. Again, it was motivated by physics. In this case, it was motivated by particle physics and condensed matter physics. It found many applications and signed that this is a deep idea. So this was just copied from the previous slide, making the analogy clear. However, quantum field theory fails the maturity test, because courses in quantum field theory are really different at different universities. Different textbooks emphasize different things. Some of them start from free theory, the scalar field, spin 1/2 and spin 1. Others first do spin 0 with the interactions. Some emphasize the renormalization and perturbation theory. Others emphasize more phenomena of smooth configurations, topology, and so forth. The field clearly has not yet matured. And there are indications that we are still missing big things. We're still learning new aspects of the theory. There are indications that we're still missing some big things. So perhaps quantum field theory should be reformulated. In order to clarify the situation, I'd like to distinguish two classes of presentations of quantum field theory that we should really keep distinct in our mind. The first is the traditional, uses a Lagrangian, and I'll have more to say about that in the coming slides. And the other, more abstract presentation is that we have a collection of operators, and here we include point operators, local operators, and also lines and surfaces and so forth. And we should consider the correlation functions, and they are subject to some consistency conditions that should be explored. No Lagrangian is needed for that. So let me say a few words about every one of these presentations. Starting with the abstract one, we use a collection of operators, I said already, local, line, surface, etc. And I'll use a little bit the terminology. I know that some people think very strongly about that. I'm not going to distinguish between operators, observables, and defects. For points, there isn't much of a confusion, but for lines and surfaces, some people like to call them defects. Some people like to call them operators. I'm not going to be, the point is that depending if it's oriented in the space direction or in the time direction, it should be viewed more as a defect or as an operator. I'm not going to get into that, so I'll just use them as all these terminology as synonymous. And the correlation functions must be well defined, so that if I take one around the other, I always get the same answer. This is a consistency condition. They should be mutually local. And we should also be able to place the theory on various manifolds. There might or might not be more conditions on the manifold. There might or might be more choices. There might or might not be additional parameters characterizing how we put the theory on the more complicated manifold. And there might be more consistency conditions. This is familiar in 2 dimensions, where modular invariance leads to additional consistency conditions, more than just the condition that we see on the sphere. And there is a question of whether we can recover all this information by just doing local measurements in Rn. Switching to the second presentation of the theory based on the Lagrangian. This is the more natural, the more traditional. And we can start from some classical system, which has some Lagrangian, and then we use either functional integral, canonical quantization, or other methods to quantize it. The complications really start here. I guess this is why Dennis complained, because we really need to regularize, for example, put the system on a lattice in order to make it meaningful. Otherwise, we have divergences, and the whole thing doesn't make much sense. And the thing to prove then is that the limit exists. We have to take 2 limits. One is the continuum limit, that the lattice points are approaching each other, and the second is the large volume limit, that the total volume of the system goes to infinity. So how do we pick a Lagrangian? What do we do? First, we pick some matter fields, and they involve some target space that they take values in, and there are some non-derivative couplings like potential on the target space or Yukawa couplings. And there could also be some metric on the target space that affects the kinetic term of the fields. Might be Wezumino terms, and might be others. We also add a gauge group, that gauge group G can act on the fields. There's some kinetic term for the gauge fields. Might be some Chern-Simon term. Should really pay attention to the global structure of G. Perhaps I'll have something to say about that later. And there are new theta parameters, including some discrete theta parameters that tell us how to sum over bundles of the gauge group. And so we write the Lagrangian, and then we try to solve it. So the general questions we would like to address here is, first of all, do we know all such constructions? It could be that we miss some terms. There are more terms that can be added and should be added. In fact, there will be one term I'll mention later that was added only recently, a new term in a 4-dimensional gauge theory. Second, do we know all consistency conditions? I'm far from convinced that we know all consistency conditions that need to be imposed. And then comes the question of duality. From this perspective, duality is that we have two separate constructions leading to the same theory. So first of all, do we know all kinds of constructions? And second, when do two constructions lead to really the same theory? And I'll say more about that below. So when is it good and when is it bad? So it's really good and meaningful when everything is weakly coupled. Then everything is understood. And this comes in three categories. Category number one, we have a free theory in the UV. And near the UV, the theory is almost free. So that's what I mean by weakly coupled. And it flows to something in the infrared. And here there is a question mark. So then the Lagrangian is useful. Example is a four-dimensional asymptotically free gauge theory like QCD. The second situation where this framework is meaningful is then when it's free in the infrared. In this case, we're just doing perturbation theory around that point. And again, the Lagrangian framework is meaningful. And examples are four-dimensional QED or the chiral theory of pions. So these are clearly useful examples. There's a third situation where the Lagrangian is useful, is when the theory is completely conformal for every value of the coupling constant, and it's free at some point, and then we expand in perturbation theory around that point. And for you guys, it's around this point. And examples that have been popular recently are the four-dimensional n=4 theory, or the three-dimensional Chern-Simons theory. There it's not a continuous line, but discrete points, but we expand in 1/k, pretending it's continuous. There are two-dimensional sigma models with a Calabi-Yau target space. So the common thing in all these three classes is that we have a region where something is weakly coupled, and the Lagrangian is useful. But the Lagrangians are not always good enough. So when is the Lagrangian approach? So that's when the Lagrangian approach is good. When is it bad or not useful? I would like to emphasize four classes of situations. First, when there's strong coupling. Second, I'm going to argue that Lagrangians are not used in the exact solutions. I'm going to talk about duality and theories without Lagrangians. And I'll spend a few slides on each of them. So first, the strong coupling. So given a weakly coupled theory described by a Lagrangian, I've already said that. Weakly coupled theory we can describe by a Lagrangian. There's no clear recipe how to analyze it at strong coupling. In fact, this is one of the biggest challenges in quantum field theory. Given some weakly coupled theory at short distance, what is the long distance outcome that comes from it? So here are some examples. Like QCD, there is a gap in the spectrum. We start at short distance with free gluons. We end up in the infrared with interacting glue balls with a gap. We'd like to understand the spectrum of the glue balls, how the glue balls interact with each other, and we don't know how to do that. Even in simpler theories that are conformal field theories, we don't always know how to solve the theory if the theory is conformal. For example, the Ising model, there has been enormous progress recently in the three-dimensional Ising model, but there are no clear analytic methods that give us the answer. So we write a Lagrangian, the Lagrangian flows to something, but the Lagrangian is not that useful. And even for simpler theories, so there is a hierarchy here, kind of full, complete interacting theories, conformal theories, and then topological theories. There are techniques to solve them, but the techniques usually are not based on the Lagrangian. So the challenge is how to solve the theories for small values of k where they're strongly coupled. This is related to the other point that even when we have a Lagrangian, we rarely use it when we make exact statements. The exact solution of the theory doesn't use the Lagrangian. So we write a Lagrangian, we are very happy that it exists, then we throw it away and we solve the system using other methods. So in this case, what we really use is the more abstract presentation of the theory. Instead of the Lagrangian, we think that, well, we have some correlation functions. They have to satisfy some consistency conditions. Let's look for a solution of the consistency condition. So here are some examples. First, bootstrap methods initiated by Sasha and his collaborators, first in 2 dimensions, and more recently, enormous progress doing that in higher dimensions, quite spectacular. And the Lagrangian is not being used. Some properties of the operator product expansion are assumed, and that gives precise numerical answer. This is quite amazing. The Lagrangian plays no role in that discussion. Then there are integrable systems, again, very strong here in Stony Brook. There's a Lagrangian but when you solve the system, you solve some other set of equations, say Yang-Baxter or something else, again, the Lagrangian plays no role. So what is being used here is a large symmetry group. There's been enormous activity in rational conformal field theory, and again, here it's a combination of these methods, a large symmetry group and some consistency condition. So we see all these as examples that the Lagrangian, nice as it is sometimes useless, even if it exists. Continuing on the list, the supersymmetric theories, they use the main trick here is to use the fact that some objects are invariant under a fraction of the supersymmetries, either half or a fourth, and so forth. And that comes under different names, holomorphy, BPS, chiral, topological observables. These observables can be computed. And again, the Lagrangian is not that important in that. Now, the way some topological quantum field theories are being solved are again using some simple rule, but not necessarily using the Lagrangian. Continuing in the list, some theories are analyzed by embedding them in string theory, and the fact that we have an ordinary weakly coupled Lagrangian plays no role. And more recently, there's been enormous progress in studying of the amplitudes, and again, consistency of the answer is the driving force rather than the underlying Lagrangian. So this is the first thing I said is that so what I said here is that even if there is a Lagrangian, it's not used in the exact solution. Moving on next to the next point that Lagrangians are not good enough is the role of duality. So I've already said that duality is a situation where we have two different Lagrangians leading to the same answer. This is an intrinsically quantum mechanical effect. And as an intrinsically quantum mechanical effect, it clearly cannot be seen in the Lagrangian because I've already emphasized that the Lagrangian is only good when it's weakly coupled. It doesn't tell us what's going on at strong coupling. This is where duality is most interesting, when it relates weak coupling and strong coupling. So I've listed some examples here with increasing degree of complexity, starting with the free field theory in 2 dimensions. There is a R goes to 1 over R duality. In 3 dimensions, 3D Maxwell theory is dual to a compact scalar. It's again duality of one free theory with another. In 4-dimensional, Maxwell theory is self-dual, but it inverts the coupling constant, so it relates small h bar to large h bar. In this case, we can do the Lagrangian because it's free. So both of them are free and free with the same variable. Although it's still a bit subtle. It's still a bit subtle because the change of variables is like a Fourier transform. So things that are localized in one are not localized in the other. But in this case, you cannot. So I'm moving to a slightly more interesting case. Remember I mentioned that this line of conformal field theories labeled by a parameter. Here duality relates weak to strong coupling. So the weak is described by the Lagrangian, but at strong coupling, the Lagrangian is not useful, but the duality is still true. And 2 examples I mentioned here are the 4-dimensional n equals 2 theory, so n equals 4 theory, and the 2-dimensional sigma model with 2 different Calabi-Yau target spaces. These look like 2 different Lagrangians, yet they give the same theory, and one is at the strong coupling limit of the other. Continuing on the list, we have situation of 2 different weakly coupled theories that flow to the same theory in the infrared. So it's a different kind of duality. The duality is before the theories were free or interacting as a function of a parameter, but conformal all the way. Here, these are 2 different theories. They're really different, but they flow to the same point. This is what in condensed matter called universality. 2 different theories flow to the same infrared behavior, but the relation between the degrees of freedom here and there are highly non-local. And examples here are in, say, 4-dimensional n equals 1 gauge theories, or 2 different linear sigma models flowing to mirror Calabi-Yau sigma models. So these are examples of that. And we can also have a weakly coupled theory in the UV, flows to a weakly coupled theory in the IR, but the degrees of freedom completely rearrange themselves. A trivial example, quote unquote trivial, gluons and quarks at short distance, pions at long distance. More complicated examples involve gauge fields. So in all these cases, there is a Lagrangian, but it's not that useful. The phenomena that the theory has, the phenomena that the theory exhibits, the Lagrangian doesn't do justice to them. There's beautiful structure there that the Lagrangian does not capture. Continuing with my case or my attack on Lagrangians, the theory is without Lagrangian. So you can lack Lagrangian, you could say, well, don't confuse me with all these things you can't do with that. Well, in this case, you're out of luck because there's no Lagrangian. And there are several different classes of situations. First, there are theories without Lorentz invariant Lagrangian. There are chiral fermions on the lattice. There are various self-dual. These theories are even free, and yet they don't have a Lagrangian. And again, because they are intrinsically quantum mechanical. And then there are various theories that we found over the last several decades that are not the strongly coupled limit of any weakly coupled theory. So we have some strong coupling theory, and there's no Lagrangian description of it at all. And they occur primarily in higher dimensions. There are non-trivial examples in 4 dimensions, and in 5 dimensions, and in 6 dimensions. And I'd like to really emphasize this point. Some people might like to dismiss them as esoteric theories. As more and more is being uncovered about them, I think it's fundamentally wrong to dismiss them. These are beautiful theories, and the fact that they don't have a Lagrangian, I think really screams that we think about quantum field theory the wrong way.
I thought that generalization of the Lagrangian is the operator product expansion.
That was what I called the other presentation, the abstract presentation. We have some operators.
Yeah, but we can deduce the Lagrangian equation. In the weak coupling, we can look at this.
Yeah. They are,
these theories you are describing, they obviously do have.
They don't have a weak coupling limit.
I know, but they do have.
Yeah, they do have an operator. So the other presentation, the abstract presentation, clearly exists, but they don't have weak coupling. So the clear way to see if there is weak coupling, there is a Lagrangian, go there. If you are at strong coupling, and either there is no weak coupling, or you don't know how to go there, or you're just stuck at strong coupling, then the Lagrangian is useless. And the operator product expansion, or the abstract presentation, is often useful, very useful, but it also leaves something to be desired.
But you can go to the lattice, and then you have a Lagrangian, and then you have a...
I really challenge you to analyze these theories on the lattice and to exhibit all the marvelous properties of duality and so forth.
No, but to just simply comment on what you just said, you can have a gauge theory, which is strongly coupled. You go to the lattice and you do a lattice simulation, and you have all kinds of results.
That's right. I agree with that. That does not strike me as a fundamental presentation of the theory.
But anyway, it doesn't not responsive to this because these are cases that don't have Lagrangians.
No, but you can imagine you can put them on the lattice and you fine-tune a trillion parameters, and then you can do the simulation. So at least in principle, you can imagine that this thing is possible. Pragmatically, I don't think it will be possible. And in any way, it will not do, I emphasize here, the marvelous properties. The Lagrangian is not going to do any justice to that. I'm sorry, now you can.
But let's see, on the other side, okay, how can you prove that, for instance, strong coupling regime is equivalent to weak coupling regime if you don't have Lagrange? You have to believe in something, or just believe?
I think, I think there is no doubt that these theories exist. There is no doubt that these theories exist.
But what is the alternative way of formulating?
Well, that's a big question. That's an excellent question, and that's the question I'm posing. I'm not proposing an answer. So I think all these suggest that quantum field theory should be reformulated. I said the Lagrangians are not good enough. I mentioned all these points. I had 1 or 2 slides on each of them. It's not useful at strong coupling. It's not used in practice with exact solutions. There is the issue of duality, and sometimes there is no Lagrangian. There are other points. I think Dennis would agree. It's not mathematically rigorous. If it's not mathematically rigorous, again, it suggests that maybe we're not thinking about it right. And I think that so many smart mathematicians worked on it for so long, and still there is no answer. It's not their fault. It's our fault that we don't understand the theory well enough so that it can be made rigorous. And I think not understanding it well enough is really the statement that there must be another perspective. And the next argument that it should be reformulated is that there are various extensions of traditional local quantum field theory that are not traditional local quantum field theory that still exist. They're generalizations of quantum field theory. I mentioned some examples here. The theory on a non-commutative space It does not satisfy all the axioms of quantum field theory. And there's this enigmatic object that came out of string theory, the little string theory, which does not have gravity. It's clearly interesting. It's clearly a generalization of quantum field theory, and we don't know what it is. Now, I mentioned that this is the third time I give a version of this talk. And the first two times, a question came up about a comment of Landau. So I thought I could really clarify that. So this is Landau, the hero of many of us. And in 1960, he said, we are driven to the conclusion that the Hamiltonian method for strong interactions is dead and must be buried, although, of course, with deserved honor. So this is the quote I found translated to English. That's correct. He said Hamiltonian and not Lagrangian. So you looked at my slides. So this is the quote. And I think once Sasha complained with that. And the other time, I think it was Linde complained with that. And I'm sure there's some other person in the audience of Russian origin who could also bring that. Now, let me say a few things. First of all, he talked about Hamiltonian and not Lagrangian. That's very fundamental and very important. My attack here is on Lagrangian, not on Hamiltonian. Number two, he thought that the theory is wrong, not that the formulation. I have no problem with the theory. The theory is right. I'm only attacking the formulation. So in that sense, I'm really different than Landau. So here, the theory, and I claim that the theory and its current formulations are right. There's nothing wrong with our current formulation. It's just not good enough. And the Hamiltonian I claim exists. The problems are with the Lagrangian, not with the Hamiltonian. And therefore, we should just look for a better formulation.
Why do you think there is no problem with the Hamiltonian?
Because the Hamiltonian, so Sasha would tell you that the operators make sense, and there's an OPE and so forth. So there is an energy momentum tensor. And once there is an energy momentum tensor, it's one of the operators in the list of local operators. I can integrate it over space and find the Hamiltonian. So the Hamiltonian as an operator exists. It's this whole Lagrangian point of view that I have difficulties with.
I can't resist adding to this quotation to quote another great physicist, Topological,
Yes.
who said that the Hamiltonian was buried, but they forgot to put the Aspen state.
I agree with everything, including the fact that Zamolodchikov is a great physicist.
Excuse me, do you still assume that the Hamiltonian is a local function of fundamental fields?
My problem is with fundamental fields.
Yeah.
Local in what? I don't know. The whole point that there are some fundamental fields that you later use in the Lagrangian, I think this is the problem. In duality, for example, you and I might describe the same theory, and what you would call a local field, I would call a non-local field, and vice versa. By the time we end up with the local operators, nice gauge invariant operators, then we'll agree. But the dictionary is non-local. So the problem is with writing things in terms of local fields. Ed?
So I just wanted to clarify when you said you actually answered that. Okay. Fine.
You would put in a list of axioms that the stress tensor always exists.
Yes.
So this number one is it.
Maybe 3, but it is in the list.
What is it?
There are some operators. The identity operator exists. Yeah, there are.
Now, what about classical limit?
Well,
In classical limit, we have Lagrangian.
yep. So I emphasized more than once that the weak coupling, the Lagrangian is there and useful and so forth.
Theories which have weak coupling, they don't have classical limit.
Yep. These theories are intrinsically quantum mechanical. They don't have a classical limit. And therefore, even searching for a Lagrangian is not a good idea because they don't have a classical limit. They are not even a deformation of a weakly coupled theory. Some theories don't have a classical limit, but they started their life at short distance in the classical theory with a small interaction. Some of these theories, are not, like these high-dimensional theories, are not like that.
Well, there's a case. Take gravity, right? Then, when you are making perturbation theory around certain backgrounds, and okay, it's weakly coupled theory, you can calculate up to renormalizability cross sections. But how you are going to get different backgrounds without having Lagrangian theory?
Yeah. First of all, this is an interesting question, but I'd like to say because. Well, I'll soon say why it's an interesting question, but I'd like to say that what I ask myself is what is quantum field theory, not what is quantum gravity. That's a separate thing. when you enter gravity, a whole new collection of questions come in. Now we know that gravity and quantum field theories are intimately related.
But take also gauge theories. There are solutions like instantal, there are solutions like monopoles, okay? And without Lagrangian, I do not know how to get.
Yep, that's why it's challenging. But in some dual description, the monopole could be a fundamental field. It's not a classical solution of anything. It's a fundamental field in the dual description. And the instanton of one theory have nothing to do with the instantons of the dual theory. The instantons and the finding classical solutions, these are extremely powerful and useful tools in some framework.
And I think what he's asking, how to change the background if we don't have a Lagrangian. How we
It's not states. I think that's not states.
No,
Well, if you want to take quantum field theory, should be formulated on every classical metric background. Infinitesimally, you do that by, as we discussed, the energy momentum tensor exists. You insert the energy momentum tensor perturbatively. You can even put it in the action and have the same theory in curved space. You don't need to have a Lagrangian in order to ask the question. It might be hard to answer in practice, but
what can you write then in the background without symmetries, even for correlation functions? If, for instance, you have something like de Sitter, you could actually use symmetries of the background. But if you take arbitrary background without symmetries and you are interested in that.
well, if it's a deformation of the theory, imagine you know all the correlation function. Somebody hands you all the correlation function. Now you can deform the background by putting in the exponent the energy momentum tensor and expanding in it and using the correlation functions that you know to deduce the answers in curved space. So this is a big question, and I do not know how to think about it, but let me make some comments how we could start thinking about it. So, as I say, of course, I don't know the answer. So I pose that more as a question. This is what Lars wanted. There will be questions. So.
Does it make sense to say, give me the correlation functions? Does they have to be functions of something?
Yeah.
You specify. So you've already made a choice.
Yeah, so I can say, imagine I have a list of operators, an index I runs through them, and I insert them in points in R4. So have correlation function, put operator number 7 at this point, operator number 15 at another point.
R4 has meaning.
Yeah, so I assume there is some underlying geometry, and there is a quantum field theory on that. And the answer should satisfy some consistency conditions. For example, if I take one point around, the answer is just a function of the choices of points, for example, but then there are others. There are many others. Duality.
Yes, the very topological extension in this theory.
In which theory?
In this Lagrangian theory.
Well, we know a lot. So, for example, in the 2-0 theory, we know a lot about the correlation functions. People even here at Stony Brook, people work on doing it numerically.
Yes.
Yeah, Leonardo. So there's no Lagrangian, and this doesn't stop him from putting it in the computer and solving for the correlation function.
It's also it's your modular, right? These are not just one function or so. You have a bunch of modules.
There are many issues, but if you put it on compact space-time, you don't need to. There's a whole story, and I tried to squeeze that into 2 slides. 3. So how should we think about it? And this is the bridge to my second talk. So I said there are 2 talks. One is kind of more general, and the other is more technical. So I think a good place to start is a topological quantum field theory, because a lot of the complications of ordinary quantum field theory are not present here. And there's been enormous progress so it's simpler, and there's been enormous progress, and it can even be axiomatized, and some people like it more or less, but that's very useful. But what about theories which have local degrees of freedom? So I'd like to make a little step into the theories with some local degrees of freedom by suggesting to look at topological observables in an ordinary quantum field theory. So imagine you have an ordinary quantum field theory with all its local little excitations and complicated correlation functions that are not topological, but you're lucky, and a subset of the observables are topological, so that you move them a little bit and the answers don't change as long as you don't touch another one or you don't change the topology. So theories with global symmetries have topological observables, and therefore I'd like to focus on theories with global symmetries. And I'll follow 2 papers with Anton. One with Anton. In fact, the title here was precisely that, coupling an ordinary quantum field theory with a topological quantum field theory, something like that. Maybe I got this backwards. and another paper with Gaiotto, Kapustin, and Willett that came out last December. So, but before I do that, I would like to make some general comments about global and local symmetries, but just to put things in perspective and to be more accessible and to make sure that we are on the same page. So there are global symmetries and local symmetries, and some things are the same and some things are exactly the opposite between the two columns. Global symmetries are intrinsic properties of the quantum field theory. I can take this abstract presentation. I don't need the Lagrangian. The global symmetries exist. I might or might not know how the global symmetries act on the fundamental fields, but I don't even need to have elementary fields to understand global symmetries. They just exist. Gauge symmetry is ambiguous. That's the whole point of duality. We have two different Lagrangians with two different gauge symmetries, and leading to the same theory. Global symmetry can be accidental in the infrared, in which case it is approximate. So the gauge symmetry can appear only at long distance, but then it is an approximate theory that there are high dimension corrections that violate the symmetry. Gauge symmetry can also appear in the infrared, but then it is exact. So this is similar. It can appear in the infrared, but it's exact here and approximate here. We use global symmetry to classify operators. In the case of local symmetries, all the operators are gauge invariant. Since all the operators are gauge invariant, this is not really a symmetry. It doesn't act on anything. So we can call it gauge redundancy. It's very useful when we try to write a Lagrangian and do certain computations. But if we look at the presentation of quantum field theory in terms of points, lines, etc., the gauge symmetry is not there. Otherwise, there couldn't have been duality. The gauge symmetry had been there. The global symmetry can be spontaneously broken. I'll say more about that soon. Here, the local symmetry cannot be broken. For one thing, it's not a symmetry, and since it's not a symmetry, it cannot be broken. But second, the local symmetries are spontaneously broken as a phenomenon of large volume. We are in the infinite volume limit, and we have to do certain transformation on all of space. Gauge symmetry transformations act locally in space. We don't get this infinity of space, and therefore they cannot really be spontaneously broken. Now, if the symmetry is unbroken, we can use it to classify states. That's one use of the global symmetry. Here we don't classify any states because there is no symmetry and all the states are gauge invariant anyway. So if it's unbroken, we can classify states. We can classify operators whether the symmetry is or is not spontaneously broken. It's useful to classify phases, and again going back to Landau. Landau told us how to classify phases. At his time he said we have some global symmetry at short distance. There's some order parameter that transforms under the symmetry. The order parameter might or might not get an expectation value. And when it gets an expectation value, the symmetry is spontaneously broken. If it doesn't get an expectation value, the symmetry is not spontaneously broken. And this is how we characterize phases. So this was Landau. And there's none of that in this column because there isn't really a symmetry. In this case, 'Hooft anomalies make sense. Use the phrase 'Hooft anomaly, although I'm sure he was not the first to say that. When we have so imagine you have three global currents of a global symmetry, there could be an anomaly between them. And this anomaly allows us to constrain what happens in the infrared. So this is a useful property of global symmetries. Local symmetries cannot be anomalous. Now, in the presence of gravity, none of these exist. And it seems that for the standard model of particle physics and for gravity, the gauge description is essential, although I would like to advocate that even that will disappear. So this is my comparison of global and local symmetries. And now let's go in a little bit more detail and focus on the global symmetries. So the point of view I'll take from now is the non-Lagrangian point of view. I have this abstract quantum field theory with some local operators, line operators, etc. And I'd like to understand their global symmetries. Yes, but I would act, well, for most of this talk, I would not assume unitality. I'd be happy to assume it. It would not be essential for.
But in the gravity case, actually, we have a metric, right, which breaks the homomorphism or something.
Well, I won't be surprised if the fundamental description of nature, there is no metric in the fundamental formulation. This would be some emergent concept which is only approximately defined long distance. I think there's enormous evidence that this is right. So what is a global symmetry? It's something that acts on local operators. And if the symmetry is unbroken, the charged states are particles. So we are going to generalize it to generalize global symmetries. Very similar, except that the charge operators are not going to be local operators inserted at points, but it could be lines, surfaces, etc. And if the symmetry is unbroken, which I'll say exactly what I mean by that, the charge objects are strings, domain walls, etc. So we'll bump everything 1 or 2 dimensions up. Now this is intuitively clear, and you will see that many of the notions I'll be talking about, you will think that, oh, we've already known that. And there are various connections to things that are already in the literature. But I'll try to make it a little bit more precise, and I'll get new perspective on known results, and I will also have a bunch of new results. So what we will do is we'll take our favorite, say, quantum field theory textbook, see whatever is being done with ordinary symmetries, we have the opportunity to do it again for these generalized symmetries. Now, the gauge version of these symmetries are very common both in mathematics and in physics. In physics, as far as I can tell, the first time it appeared was in the Karl-Bramon field in string theory. And in lattice gauge theory, it appeared in the Villain formulation of lattice gauge theory. Then it appeared very commonly in supergravity. They are higher form gauge fields. And especially in more recent developments in string theory, and the charge objects are these D-branes and other kinds of branes. There's a lot of that. In mathematics, it comes under the name of Chigger-Simons theory. But I would really like to emphasize that I'm more interested in the global version of that before gauging it. First, because logically, we should first study the global symmetry before we gauge it. The way we study quantum field theory, there's a global symmetry, and then we gauge it, rather than just study the global symmetry, rather than just jump ahead to the local symmetry. And second, as I already said before, these symmetries could have anomalies. So we can have a global symmetry with anomalies. That has consequences. So we cannot even gauge it. And this obstruction to gauging is interesting. So for these 2 reasons, I think we should really study the global symmetry rather than directly jump to the gauge symmetry. So I'll have one review of global symmetry and say it in a rather obscure way, but way which makes it easy to generalize. So ordinary global symmetry, I'll use the abstract definition. These ordinary global symmetries exist whether we do or do not have a Lagrangian. So how should we study? Somebody hands us correlation functions of local operators. How can we tell that there is a global symmetry in the problem if we don't have a Lagrangian? Sorry? If it's continuous, and what if it's not continuous, for example? So I'm going to give a formulation that gives both of them, puts both of them together, and both discrete symmetries and continuous one, and you'll see where the current is. So I'll pick a manifold. So we have some space-time, and we'll pick a codimension 1 manifold M, and we'll say that the list of operators in the theory, all these points, lines, etc. operators, includes operators associated with codimension 1 manifolds M. Oops. Codimension 1 manifolds M, and they are labeled by group element little g. So, and these objects have some properties. The correlation functions of these objects are topological. So this is a codimension 1 manifold that I can slide a little bit without changing the answer. That's the first property. And they can be multiplied this way. So I multiply 2 of them, one with group 1 and one with group 2, and I get the element of group 1 times 2. So more physically, you're actually familiar with that. This is the charge. More precisely, this is the e to the I times the charge. And what this operator does, if M is all of space at fixed time, it's an operator that acts on all of space and performs the transformation. In 2 dimensions, we are used to that. We have local operators, and we can integrate a current around it. If we exponentiate it, we find this U, and it implements the transformation. Well, that would just mean that the group law is a little bit different. There's a group. Somebody hands cosine with you have some other group in mind, and you realize that there's a group. somebody hands you, Sasha solved the theory, and he gives you the list of all correlation functions with all the surfaces and all the volume operators and so forth. And you recognize the subset of operators that are topological and multiply like that. That's the condition. And local operators are such that if they are inserted at a point P, are surrounded by, say, a codimension 1 sphere surrounding it, and it appears in some representation of the symmetry group G. So this is how they act. So M surrounds P, and we're using that, we can get Warden entities. Now, if the symmetry is continuous, this U can be written as e to the I, an integral of a current, and that's the answer to your question, Nikita. When the symmetry is continuous, we can extract this operator J, which is a local operator, but more generally, this is the thing we should do. So J is the...
G is exponential of epsilon, and then you write exponential J times epsilon.
Well, I can absorb epsilon in J.
Yes. No, he said that it has to be the algebra.
Well, but I also put the parameter, I absorb the parameter in J. My J includes... would be a little bit more complicated. But I think what I wrote here is mathematically correct. So I'm going to generalize it, and the generalization is straightforward. Now, intuitively, we're thinking about lines and surfaces, and the words you often hear. So imagine you want to define it for strings. You ask, what is the symmetry of strings? So you say this is the operator, the charge, has an index, mu, associated with the direction of the string. But then Coleman-Mandula tell you that you cannot have charges with an index mu. That violates Coleman-Mandula. But then you realize that the charge is actually infinite. So what you should be discussing is charge per unit volume. But the charge per unit volume becomes a little bit confusing. What if the string moves around? What if it wraps a cycle? What if the topology is complicated? So instead, I'm going to replace it by the following thing. I copied the previous slide. And wherever I had codimension 1, I now wrote codimension q plus 1. So the same is true, except that M is of higher codimension than before. And there's still a group element. So ordinary symmetry is q equals 0. And U depends on the group element little g, and a higher codimension manifold M. And everything else is essentially the same. So the correlation functions of this gadget are topological. I can multiply them, and they form a group. But I emphasize that because of the high codimensions, the order of the multiplication doesn't matter. Because before I had codimension 1, so I can multiply in this order or in that order, and that's a different thing. Now there's a higher codimension, so I can slide one through the other, and therefore the order doesn't matter, and therefore the group should be abelian. I should emphasize that in the gauge version of this problem, people always ask, what's the non-abelian version of B mu nu? And it has always been a puzzle how to do that. And in lattice gauge theory, people try to do that, and there are various difficulties. But it looks like it's a difficulty. We were not clever enough to think of a solution. If we only could come up with a better solution, we'll answer it. From this point of view, just saying that in the global symmetry, we have something of higher codimension, it's clear that there's no room to look for a non-abelian version because of this property. So the charged operators, these are the charges, and the charged operators are V of L. They are of dimension Q manifold, L. For a good example to keep in mind is 4 dimensions with a one-form symmetry, Q equals 1 in 4 dimensions, and then these are lines and these are surfaces. And as before, when M surrounds L, we have a representation of the group, and V is in a representation of the group. So since the group is abelian, R of G is a phase. Continuing with the slide of ordinary symmetry and generalizing it, if the symmetry is continuous, we can exponentiate it and write it as an integral of a local density. And J is a closed current. And it has a property familiar from the theories of branes. If you compactify, say, on a circle, a Q-form symmetry splits to 2 separate symmetries, a Q-form and a Q-1 form symmetry in the lower dimensional theory, depending on whether this manifold, M that I had, does or does not wrap the circle. And I emphasize again, no need for Lagrangian. Nowhere did I say anything about the Lagrangian. This thing exists abstractly, just the correlation functions of operators and surfaces and so forth. And that's why it's useful in the case of dualities, because these are intrinsic properties of the theory. Again, I emphasize, no need for Lagrangian. It is intrinsic. This is a property of the theory, does not depend on the presentation. So what do we do with this? We do all the things we ordinarily do with ordinary symmetries, except that we have the opportunity to do it again. The first thing we do with symmetries, we can get selection rules on amplitudes. That's the first thing we do with symmetries. I think the simplest of them has already been found by Witten, arguing that the Wilson line surrounding a non-trivial cycle in the manifold has a vanishing vacuum expectation value. We can think of others. We can couple it to classical background field. These are twisted boundary conditions. And I got to say that here I was quite confused for many years. Many people in the audience probably were not confused. Most people in the audience were not confused. I was confused. 't Hooft studied the four-dimensional gauge theory with twisted boundary conditions. And I got to say that I was always confused. Was he talking about the SUN theory or the PSUN theory? That wasn't clear to me, because he used a PSUN bundle that is not an SUN bundle. But if what he was interested in was the SUN theory, then this bundle should not be considered in the first place. And if what he was interested in was the PSUN theory, he should sum over all these bundles. So I'd like to advocate that this twisted boundary condition theory is an observable in the untwisted theory. So this is an observable of the SUN theory. So we don't need to sum over all the bundles. This is a property of this. The same way we think of ordinary symmetries, say in 2 dimensions, it's very common. We have a global symmetry. We can consider twisted boundary conditions. This is an observable in the theory. And if we sum over twisted bundles, then this is what we call the Oberfold, i.e. gauging the symmetry. So this is what I started saying. We can gauge this symmetry by summing over the twisted sector, like Oberfolds. And here we find new parameters, because this is familiar in 2 dimensions, this phenomenon of discrete torsion. We can have an Oberfold. We sum over the twisted sectors, and there are more than one way of summing the twisted sector associated with what is known as discrete torsion. There's a 4-dimensional version of it in non-abelian gauge theories that was found here. So this is a discrete data parameter. Now, dual theories have different gauge symmetries, but the global symmetries have to be the same. And this was studied in detail, both in n equals 4 and in n equals 1. This thing about tests of duality. So we have different theories. They have different Lagrangian, maybe even different gauge group. The global symmetry should be the same. So here we have an opportunity for a new test of duality, a test that was not done before. So sociologically, whenever you already have the duality and you come up with a new test, it's much more impressive than the tests that were there designed to work by the duality. And it works in flying color in a somewhat non-trivial way. And I would like to emphasize that since we're talking about lines, that we map lines between different theories, this goes beyond BPS operators. So this is a comparison of non-BPS operators between dual theories, and that makes it less trivial. I'd like to use that also to characterize phases. I've already emphasized Landau's characterization of a phases based on the global symmetry. There's a global symmetry at short distance, and it either is or is not spontaneously broken. And then in the 70s, 't Hooft and Wilson had an orthogonal development, another way of characterizing phases, using the behavior of the Wilson and the 't Hooft loop, whether the loop does or does not have an area law. And that looks like it's orthogonal to Landau's story. Landau talked about the symmetry that is either spontaneously broken or not, in some local order parameters, and here we have a loop that does or does not have an area law. It looks totally orthogonal. I would like to emphasize, and the point I'm going to make now, is that the Wilson and 't Hooft characterization is essentially the same as Landau's characterization, except that for these generalized symmetries. So we just repeat what Landau said, but for the generalized symmetries, and we will recover the Wilson and 't Hooft characterization. So in a confining phase, claim that there is an electric one-form symmetry that is unbroken. And the picture of that is very similar. They are confined, if there is confinement, they are confining strings. They are charged, and they are classified by the symmetry. And I already said that states that are classified by the symmetry is the hallmark of the symmetry not being spontaneously broken. the symmetry is spontaneously broken, we cannot classify the states. The order parameter is a large Wilson loop. So if there is an area law, can make the Wilson loop very large. Its VEV goes to 0, very much like in Landau's story. Separate charge operators, and the expectation value goes to 0, hence the symmetry is unbroken. And finally, we can compactify 4 dimensions on a circle to 3 dimensions. And the one-form symmetry becomes an ordinary symmetry in 3 dimensions. And in the confining phase, this symmetry is unbroken. This is another thing that I was always confused about. Polyakov and Susskind tell us that in 3 dimensions, when we compactify SUN gauge theory to 3 dimensions on a circle, there is an exact ZN symmetry, global symmetry, an exact global ZN symmetry in 3 dimensions. I already said earlier that we can have accidental symmetries in the infrared. It's very common that as we go to the infrared, we find theories that are not there at short distance. But in that case, these accidental symmetries are approximate in the infrared. If we just look high enough, either at higher energies or with higher precision, we realize that the symmetry is not exact and it's violated by something. So I've been confused about that from the time I was a graduate student and I read this thing. How come the low energy observer sees an exact ZN global symmetry without anything in 4 dimensions, without anything in the shorter distance theory? Where did this exact global symmetry come from? A symmetry that persists to arbitrarily high energies. It's an exact symmetry. And the answer is that it has a 4-dimensional precursor, but it's a one-form symmetry. So there is a global symmetry already in R4, this one-form global symmetry. And that symmetry is unbroken. This is confinement. In 4 dimensions, I don't need to compactify to see that. What about the Higgs or Coulomb phase? I'm going to renormalize the perimeter law that is not universal to 0. And then, as I make the loop very big, it goes to a constant. This looks a lot like Landau's description of the order parameter getting an expectation value. Take a charge 1 and charge -1 operator, I separate them. There's a non-trivial expectation value. The fact that the loop doesn't go to 0 when it's large is the statement that the symmetry is broken. Second sign, no string. And again, following Polyakov and Susskind, we compactify on a circle. The symmetry becomes an ordinary symmetry, no longer a one-form symmetry. And then in this phase, it is spontaneously broken. So all these things fit together. So the one-line summary, unbroken symmetry is confinement. Broken symmetry is Higgs or Coulomb. And broken or unbroken, very much like Landau. So what are the consequences at low energies of if the symmetry is broken? If the symmetry is unbroken, we see strings at high energies. But what if the symmetry is broken? So if it's continuous, we have a Goldstone mode, very much like with ordinary symmetries. So a spontaneously broken one-form symmetry must lead to a massless gauge field. So for example, there is a photon in the Coulomb phase. We all know this matrix element, a photon with momentum p and polarization epsilon. This is F mu nu, this is the current, and this is the vacuum. And that looks a lot like the matrix element for pions. So it's natural to interpret that as being the statement that there is a symmetry, it's spontaneously broken, and the photon is the Goldstone mode of that symmetry. So that's if the symmetry is continuous. What if the symmetry is discrete? A broken discrete one-form symmetry leads at long distance to a topological quantum field theory. Example, if we have a Zn one-form symmetry, at low energies we have a Zn gauge theory. So a low-energy observer can really detect that there is an unbroken Zn global symmetry, one-form global symmetry, by finding a topological field theory at long distance. So this is what our friends in condensed matter physics call long-range topological order. We can have a gap, and still there are correlation functions with long-range order. And the last point I would like to make is higher form SPT phases associated with anomalies.
Before that, what about supersymmetry?
Supersymmetry is the orthogonal description. Everything here can be supersymmetrized. In fact, in the examples with supersymmetry with n equals 1 or n equals 4 in 4 dimensions, this story fits very nicely.
I meant as a global symmetry.
Supersymmetry, if you don't have gravity, it's a global symmetry. But it's a spin 1/2, not spin. There might be spin 3/2. I don't know anything about that. That's an interesting point that I didn't know. So there could be anomalies. This is a SPT phases is a hot topic in condensed matter physics or statistical mechanics. So consider a system with an unbroken symmetry, a global symmetry that has a 't Hooft anomalies. So recall, gauge symmetries cannot have anomalies, but global symmetries can have anomalies. So the 't Hooft anomaly matching conditions constrain the physics in the infrared. And depending on the details, they constrain the physics in different ways. They either force us to have some excitation, massless excitations in the bulk. There might be some excitations only on the boundary. And it might even be that we have nothing in the bulk, not even a topological field theory, kind of a unique state there, but there are some boundary modes that are there. So this comes under the name of symmetry-protected topological phases. And it's particularly interesting either when we have a boundary or we have a domain wall between different SPT phases. In that case, when we have two different SPT phases, on the domain wall, we could have excitations because the anomaly is different on the two sides of the wall. The anomaly is different, so there's a phenomenon of anomaly inflow to the wall. So here is an example. N equals 1 four-dimensional Susy-Young Mills, SUN, has n vacua associated with a spontaneous breaking of a discrete R symmetry. So there are n vacua, but they turn out to be in different SPT phases. So there's a one-form symmetry in SUN associated with the center of SUN. There's a ZN one-form symmetry. And its anomalies are different in the different vacua. More microscopically, it comes about because the object that condenses in the different vacua is always a magnetic monopole, but it's a magnetic monopole with different electric charge. Since it's a different dion in the different vacua, these vacua have different have different anomaly in the ZN symmetry, and therefore they have different anomalies. There's anomaly inflow, so there must be something on the domain wall to saturate it. And the thing that saturates is a UK level n Chern-Simons theory. This is a three-dimensional domain wall, where k is the integer that counts by how many vacua we jump. So in the simplest case, we jump between, the domain wall is between two neighboring vacua, in which case we have just U1 level n on the domain wall. Now, this particular answer had already been found by Achara and Vafa using a string construction, but I must confess that I did not understand whether their result was a consequence of the string theory we embedded it in, or whether their result was intrinsic to the quantum field theory. So now we see that the quantum field theory has an anomaly forcing this construction. There's a Z2 and R symmetry broken to Z2, which labels the vacua, and K is the difference between the two vacua. So in conclusions, higher form global symmetries are ubiquitous. They occur all over the place. There's a long list of examples in our paper. They can help us classify extended objects like strings and domain walls. Just as ordinary symmetry classifies operators, these classified line operators or defects, line surfaces, etc. They are useful in duality because unlike gauge symmetry that is different on the two sides of the duality, the global symmetry must be the same. That's also true for these global symmetries. And we have discussed the extension of Landau's characterization of phases based on order parameters that break a global symmetry. And we showed how Wilson and 't Hooft's characterization fits into that. I should emphasize here that this discussion in terms of groups makes the whole description of confinement and oblique confinement and all that a lot more streamlined. And it's a lot easier to analyze the system. And in fact, some mistakes in the literature are easily uncovered using this way of thinking. Finally, I discussed anomalies for ordinary symmetries and for these generalized symmetries. There could be a 't Hooft anomaly matching. There's anomaly inflow. And I showed that there are degrees of freedom on domain walls. So I've already summarized the first half of the talk, where I emphasized that quantum field theory, beautiful as it is, should be reformulated. And this is an infinitesimal, perhaps negative infinitesimal, but the infinitesimal step in this direction. So thank you for your attention.
Thank you.
your ideology, as I would say, to one useful example, QCD, namely, okay, and then in this confining region. First, I could think that maybe it's hopeless to try to get the spectra of the mass of the hadrons using this fundamental SU3, Lagrange. Because without Lagrange, I do not know how to get numbers. But what is the other way to get numbers if I don't have Lagrange? Because numbers do not come from anywhere.
Yeah, well, so the best way as of today to get numbers at long distance, at short distance we're just doing perturbation theory. At long distance, the best way today is the lattice. Put the system.
Lattice is using Lagrange?
Yeah, the lattice uses the the Lagrangian.
Yeah.
Yet, the lattice, again, leaves a lot to be desired. Some of the symmetries are not manifest. We have to prove the limit, that the limit exists. And the calculations are kind of messy. And although the accuracy has been improving dramatically, this does not look like a conceptual presentation. Now, it might be that I strongly believe that there's another presentation of quantum field theory. That other presentation might or might not be helpful in solving QCD. But it might also be that there's another presentation of quantum field theory in which there is no lattice, the existence of the theory is rigorously established, and at least some qualitative features like the mass gap in few gauge theory is established. In fact, this is one of the Clay questions. To do exactly that, right? So the question you're really asking, solving this Clay question will give the answer to your question. Yes?
Yeah, because without that you don't get million. Without using Lagrangian for SU, right?
Well, Ed wants to say something.
Are you foreseeing a new formulation of quantum field theory in general, or just a new formulation that's useful for some classes of theories, where existing formulations?
Well, since speculations are free,
Yes.
I would say that. So in the maximal version, there's a new formulation that makes a lot of the existing discussion totally obsolete. Calculations are easier, results are manifest, the mass gap is manifest, and so on. Okay, having established that, now I can start negotiating and, and prove less. But I think that thinking about it would be useful, and it might be that new formulations will be better for one questions and not another. I should also emphasize that since we now understand that quantum field theory is the same as string theory, a new formulation of quantum field theory might also be, as part of the same package, will give us a new perspective how to think about string theory. But I have nothing useful to say about that.
John?
Are you happy with the way the standard model is conventionally presented, or do you think we're using the wrong words?
I think we are using the wrong words. It's very useful because it's weakly coupled. So in TeV range, we use weak coupling, and that's good enough to do calculations. So pragmatically, it's perfect. And if we have more powerful computers, we'll even get the QCD spectrum. So why bother? It is bothersome that the theory that we think is so fundamental, we cannot give a non-perturbative formulation of it, putting it on the lattice, because it has this chiral spectrum that we don't know what to do with. There are other conceptual issues. And we are doing physics not only in order to get numbers that can agree with the experiment, but also in order to get more qualitative insights that would guide us forward. And I think this is really a big gap. Where did this standard model come from? So maybe a better formulation would shed light on that. I don't know.
Yeah, I thought from the beginning of your talk you were looking for a formulation that would be analogous to the conceptual pleasure that calculus gave to that part of the history. So it makes that pleasure is independent of whether or not you can compute numbers or solve a particular problem. It's like an intellectual pleasure. I thought that was what you were asking for.
Yep.
You can ask practical questions later.
Yeah, I fully agree with that. So this is, thank you for saying that. This is the answer to, say, for example, your question. One thing is how to compute, and the other thing is to understand more deeply what it is that we are computing. I think this is still...
Be exactly the same that you have now when you have a conceptual.
I think historically, whenever there is a better conceptual framework, the applications come in. That's kind of the icing on the cake. But the main thing is the
motivation.
That's right.
Maybe.
That's right. But also, conversely, sometimes looking for better calculational schemes also lead you to the conceptual. So I don't see them as two separate things. They usually come hand in hand.
Lars, then Nikita, and then
Suppose you have a function integral, and you make some very complicated change of variables. Wouldn't you be able to go from one theory, say, to the dual theory?
Okay, excellent question. In the free theory, we actually know how to do it. In the interacting theory, you can't imagine how much time I wasted on this problem. And got zero progress, zero, nothing out of it. And I think that the reason I did not make any progress is that this is the wrong direction. I think thinking about it, sorry?
No.
No, I took the only available method, and with that method, I couldn't solve it. Now, maybe some smart graduate student in the audience will be able to do it. I really think that thinking about it in terms of the functional integral is not the right way. This is intrinsically quantum mechanical. The functional integral with some action in the exponent assumes some kind of a classical limit. There's a parameter h bar there that you can tune to be 0. It assumes things that you really don't want the answer to have. So something else should replace it. So the 2-0 theory is a good example. There's no functional integral. The theory exists. And it seems like duality really follows from the 2-0 theory in a deep way. And this language with the change of variables in the functional integral is not good there.
So I know it succeeded myself.
okay, well, Nikita.
In this abstract presentation of quantum field theory, when you're given a list of operators labeled with some labels, most points in space-time and line surfaces, do you think the duality might also treat all labels to be computing, exchange points and surfaces?
No, I think the duality is a redundancy in the Lagrangian. It has nothing to do with the answer.
There's no Lagrangian, so we are now in this abstract.
Then there's no duality. If what you're given is a set of correlation functions, the question of duality is not there. Duality exists only when, for a given such thing, you find two different Lagrangians that give you that.
What if you and I use different labels for the same operator?
Okay, that's a trivial dictionary.
Yeah, but now the question is, so could this dictionary be non-trivial? Could it exchange points with surfaces?
I don't see that. In all the examples of duality we know, there are local operators, there are line operators, and they are mapped. There's a map from this local operator.
We already have an answer.
Sorry? What's the answer?
Well, very good.
No, but I think if you in these examples in quantum field theory, points go to points and lines go to lines. If you have Poincare duality, you have a relation among them, but it's not. No, this is a property of the correlation function. Duality is often that you have two different ways to present the same lines. I say it's a Wilson line, you say it's an 't Hooft line. That's what duality is.
I'm asking different questions.
Okay, I do not know.
We extend duality to
That's okay. That would be interesting to do. I'm skeptical, but I'm always skeptical about everything. So.
But just a comment. You mentioned it briefly, but partly in answer to Slav's question. So it's worth mentioning that the world's most precise determination of critical exponents of the three-dimensional Ising model are now done purely by abstract Husserl methods, from essentially pure thought and computers with no Lagrangians.
And most of the minimal models do not have a good description.
Well, they have this Landau Ginzburg.
Here, and then.
I just wanted to continue with your analogy with calculus. In our beginning classes, we do teach physics without calculus. Advocate the same.
Well, I think we already teach physics.
Yeah.
Pierre, I'll answer that. We also teach physics without quantum field theory.
Yeah, I want to add to Renato's question something there. So how do we come up with the list of operators if you don't know already kind of Lagrangian even if you cannot use
you make some set of minimal assumption. For example, in the 3D Ising case, you say you know the symmetry is Z2 symmetry, and you assume that there's only one relevant operator for each parity, and that's enough.
Yeah.
Following up on Nikita's question, in string theory, there are examples where wrapped brains are dual to unwrapped brains. So that would be relating objects.
Well, but that's true. But what happens is when you do that, you also use something about the geometry that is different. So this is in the context of gravity. This talk is in the context of some rigid, very big flat space-time, nearly flat space-time, very long wavelength curvature, and we put some interacting quantum field theory on that. When we also have complicated metric associated with small cycles and things could start mixing, then it will only be more fun.
Martin?
I think, I love the talk, I thought it was very interesting. I think you made one statement which is maybe a little bit overstating things, that you can't see duality at the classical level. Certain dualities you can. They amount to saying that you have two different Lagrangians, which if you look at the solutions to the equations of motion, they're the same. They can be mapped onto each other.
That's in the free case.
No, it can be a nonlinear sigma model. T-dual theories.
But T-dual theories, don't you invert some coupling constant as you do that? In your presentation of the dual
classical solutions.
Right, but that's because it's the path that you inverted is free. Whenever the theory is free, that whether it's classical or quantum is kind of misleading. What is not misleading is, in this case, it's really a Fourier transform. So what is localized in one variable is delocalized in the other. Same as with the Fourier transform. This is intrinsically, if you put H bar in this discussion, you will see that H bar is inverted. H bar of one theory is not the H bar of the other. You've set it to 1, so you don't see that. But
there are even cases which are where we know that the duality exists only classically and not quantum.
At the level of equations of motion, you can map solution uses mappment.
Well, I'd be happy to discuss it in more detail, but as far as I understand duality, it is intrinsically quantum mechanical because it inverts H bar. So if in the classical theory H bar goes to 0, on the other side H bar goes to infinity.
The same as to compare low temperature expansion and high temperature.
Exactly the same. Exactly the same.
In classics.
Well, it's in classical statistical mechanics, which is what I would call quantum 1 plus 1. Yeah, this is terminology. Yeah, this is classical statistical mechanics. I write it, you invert beta. And for me, beta is like H bar, so you invert H bar.
What Martin meant that the Hamiltonian mark is the same. So you take Hamiltonian.
So Emil has been asking.
Will you allow me to speculate?
Emil, yes.
We usually do functional integral with the exponent of the action.
I can't hear you, I'm sorry.
We usually do the functional integral with the exponent of the action, which is the place where we actually need the Lagrangian.
Yes.
But why don't we do functional integral with some other function under the integral? You may say that let's put in the exponent and logarithm, but then the action will be non-local, so it's appropriate to do instead of exponentiation. But then you may ask, why do we take exponent always? The reason for that is just because it replicates itself. If we multiply one to the other and summate over the intermediate states, we get the same. But there are other distributions which obey the same property, you see, replicating itself. So it may be that the series you are looking for are just also have integral interpretation, but with some different weight.
Yeah. So the way physicists are often taught is that it's not a big deal. You have an ordinary integral, you just turn it into a functional integral, and everything is the same. That's wrong. It's wrong for many reasons. One reason that it's wrong is that all the beauty of quantum field theory really rests on locality. Locality is what drives the show. So it's not just write an ordinary functional integral for something that is non-local. You're not likely to get something useful. It's not going to look like quantum field theory. So this whole story with the functional integral needs more assumptions. It's not just that you can put any function you want there. Locality is important. This is not to say that you need a Lagrangian.
That would be so far.